Today's the day. We're going to learn how to solder. In this video I'll be going over preparing and protecting your tip, the right and wrong ways to solder, how to tell a good joint from a bad one, reflow and desolder, and how to solder different things. With this video I'm assuming you've watched the previous videos in the series or have some basic knowledge and have all the tools and things you need to start soldering. I won't be going into detail about things from previous videos. For those of you who haven't watched any of my Soldering 101 series before, the playlist link is in the description and the cards. If you don't want to watch any of them and have no soldering experience at all, please at least watch the terminology section of the intro video, or you may have trouble understanding what I'm talking about in this video. The terminology section of that video is at 5 minutes and 11 seconds. It's the last chapter of the video. As the saying goes, practice makes perfect. The best way to practice soldering is to build stuff. I recommend cheap LED kits off eBay, Banggood, Amazon, etc. They usually cost next to nothing, aren't too complicated, and give you a visual indication if they work or not. The downsides are they usually have very cheap components which fail quickly, instructions are crap, if there are any, and most come direct from China, so depending on where you are in the world, it could take quite a long time to get to you, especially at the time of making this video. Before we talk about how to solder, we need to know how to prepare and protect our tips. This is probably the most important section of this video, so don't skip it. We'll be going through this together because, as you can see, I have a new soldering iron to play with and haven't used it yet. Soldering iron tips nowadays are normally made up of a copper core with nickel or nickel chrome plating with an iron plated tip. In the old days, before 1970-ish, they used to just use bare copper. Copper is used because it has very good thermal properties. It transfers the heat very well, but because the solder eats away at it rather quickly, the copper is then plated with nickel or nickel chrome. The solder doesn't stick very well to that though, which would make soldering quite difficult. So the very tip, which you can see by the colour and texture difference, is plated with iron because the solder will stick to that, which makes it easier to solder, but the solder also won't eat it away like it would with bare copper. But the iron can oxidise, so we need to protect it. To get the tip ready for use, we need to tin it. We do this for a couple of reasons. The first is the iron on the tip will oxidise normally, especially at soldering temperatures if we don't, which will damage the plating, and seeing the plating isn't very thick, the last thing we want to do is damage it. It's very hard to repair properly at home if it's damaged. The other reason we tin the tip is because it makes it much easier to solder, better heat transfer, more control of the solder, etc. Tinning the tip is dead simple. Get the iron up to temperature, 350 degrees Celsius for lead base or 450 degrees Celsius for lead free, then load the tip with solder, wait for the flux to burn off a bit, then clean the excess solder off the tip on your sponge. That's it. It's been tinned and it's ready to be used. We'll do it again just to be sure we coated the whole tip and it actually stuck properly though. As you can see, the solder won't stick to the rest of the tip, just the iron plated bit. Now we'll do it a third time, but we won't clean the solder off. Instead I'll put the iron back on its holder. You may be wondering why I did that. Well, with your soldering iron sitting in the holder with that blob of solder on it, you're now protecting your soldering iron tip. I know it may seem counterintuitive at first, but when you finish soldering joints and need to put the iron down, not cleaning the tip is the best way to protect it. By cleaning the tip, you are removing most of the solder, which could expose the iron of the tip to the air, which would cause it to oxidise. That excess solder on the tip is keeping it thickly tinned, which is what we want because the more solder on the tip, without going to stupid levels, the less chance oxygen has to get in and eat away at the iron. The reason we have to keep solder on the tip is because as metal heats up, it expands slightly, which opens up the structure of the metal to oxygen molecules. Once that oxygen gets into the metal, it can cause it to oxidise and rust. Only clean the tip before you go to solder a joint and not when you're putting the iron in the stand while you're still working. At first this can be difficult, especially if you've been cleaning the tip before putting it back in the holder. You need to get into the habit of not cleaning it until you're ready to use it. When you're finished soldering for the day, clean the tip off with your sponge and then, just like we did to tin it when we first got the iron, tin it again. Put a nice big blob of solder on the tip. It will probably pull to one side, but that's okay. Let the iron cool and pack it away. That blob of solder will protect it from oxidising while it's in storage. By doing this every time you pack the iron away, the tip will always be protected and will always be tinned when you clean the excess off and use it again. Remember, when you get new tips or new irons, you'll have to go through the process of tinning them the first time you use them. You can just use them without tinning them, some people do, but it's a good habit to get into to tin them, and it takes less than a minute to do it anyway, so you're not losing a whole lot of time. There's so many ways of soldering wrong, but I'm going to focus on the main one. Any other incorrect ways of doing things will probably be addressed later in the video. The main mistake people make is trying to load the iron up with solder and then wipe it onto the joint. That isn't the correct way of soldering most of the time. We don't normally carry the solder over because it's slower and more frustrating to solder this way. The proper way to solder is much quicker and easier. The flux burns off so it won't clean the surface, meaning the solder doesn't stick most of the time. You may or may not get enough heat into both the pieces for the solder to stick properly, if the flux hasn't fully burnt off, that is. Carrying the solder over usually means the solder stays stuck to the iron instead of what you want it to stick to. Remember, without flux to clean a joint, solder won't stick. If you've been carrying solder over and wondering why your joints look like crap, well, now you know. Just to throw a spanner in the works, and so people don't complain in the comments, there is a surface mount soldering technique called drag soldering where you do exactly what I've said not to. You use a specific tip, load it up with solder, put flux on the board, then drag the tip over the pins of ICs. It's pretty much the only time you'll ever carry solder over. In previous videos of this series you've seen me solder. I've done it pretty quick and haven't really shown up close how it's done, so let's see exactly what's going on. What I'm doing is putting the tip of the iron onto the pad of the board and the component leg, leaving it for a second or two so both pieces can heat up, then I'm coming in from the other side, adding some solder, removing the solder, leaving the iron on for a second or two, then removing the iron. It's pretty simple, but let me break this down and explain this whole process step by step so you can really understand what's going on. The iron needs to touch both pieces so both pieces are heated. If you don't have both pieces heated, then you could have a cold joint and the solder won't bond correctly to either surface. The iron only needs to be left on the pieces for a couple of seconds before adding the solder because of the thermal mass of the iron, in most cases, is much greater than the copper pad and component leg. It's why we use such high temperatures in the first place. We add the solder to the opposite side of the joint from the iron because solder tends to flow towards the heat, and if it melts on the other side of the joint, we know everything has been heated correctly. If you add it to the iron side, chances are you'll get more on the iron tip than the joint and it may not flow correctly. Once we've added enough solder, I'll show you soon how to tell if you've added enough. We then leave the iron on for another couple of seconds just to make sure the solder has flowed correctly and the flux has actually done its job and cleaned everything properly. This also helps the solder flow through plated through holes and make an even better connection. Then we remove our iron and let the joint cool. As I've been saying through this series, it's a simple process. It's also much faster than trying to wipe solder onto the joint. We need to be careful through this whole process though because we're using such high temperatures. From the moment the iron touches both pieces to the moment you remove it, you're on a clock. Leave the iron too long, you could lift the pad from a board or damage the component. This normally isn't a massive issue because good quality boards and components are designed to handle these temperatures for short periods. I've never lifted a pad on a board, but on LED strips, especially cheap stuff, I have. You can and sometimes do have to leave the iron on for a good 10 seconds or more. This is usually when you're desoldering, which is where you'll usually do damage. Quality of boards and components can vary, so in general, the less time your iron spends on a joint, the better. The difference between a good joint and a bad joint can sometimes be pretty tricky to see. Hopefully in the next few sections I'll give you enough information and examples so you can understand what to look for. A couple of things you can do to help you getting a good joint are using a decent soldering iron and good quality solder, preferably brand name for both and lead based in a thin diameter, about 0.56mm if you can get it. The solder is far more important than the iron though. As I've said in previous videos, with lead based a good joint will usually be shiny. It's a little more difficult with lead free, which is why most people, myself included, recommend lead based when starting out. However, with a good joint we're not just looking to see how pretty and shiny it is, although with lead based that is a very good indicator. We're also looking for a specific shape the solder should make between the board and the component leg. Once again you get to see my fantastic drawing skills. The horizontal line is our board and the vertical is our component leg. We're looking to make a little volcano or mountain shape between them. It should be roughly even all the way around. Yep, that's really all it takes to make a good joint. It's much easier said than done though, and you won't get them perfect every single time. Some won't have enough solder, others too much. Most of the time you can add a little extra where needed, and if there's a bit too much, it's okay. The problems start when you don't have enough, or you have way too much and it looks like a big blob. Another thing is plated through holes. These are holes where the copper or gold plating goes from one pad to the other because they are connected through the board. The solder should also go all the way through and connect to the leg and pad on the other side of the board, but in practice with hand soldering that can be difficult to do with every single joint. It's more designed for wave soldering. It's also good practice to check solder joints with some kind of magnifier once you've finished and clean the excess flux off. Solder joints don't just provide an electrical connection, they also provide mechanical strength between the board and the component legs. If the board is for something like a drone or a remote controlled car, the vibrations could cause a bad joint to break. Now that you hopefully know what good joints are, before we get to the bad joints you need to know how to reflow and desolder. I showed desoldering in the previous video when I talked about tools used, but I'll show it again here. Reflowing is very simple. Add some flux to the joint, then put the iron on the joint until all the solder melts. Then remove the iron and let the joint cool. That's it. Desoldering is also simple, but we do have to be careful because we need to keep the heat on a bit longer than normal. Solder wick is a braided copper wick. It's normally coated in flux, apparently, but I've always had to add more for it to work. Stick the wick on the joint, put the iron on the wick and let it, wick the solder up and away. You'll mostly go for the wick when you need to desolder because it's quick and easy, but you may have trouble with plated through holes. Solder sucker is a spring-loaded pump with a high temperature tip. You push the plunger down, put the iron on the joint, melt the solder, then put the pump on the joint and press the button to release the plunger, which will suck the molten solder into the sucker. These will normally clear plated through holes, but you have to be careful with them. These will pull pads off if the pads aren't bonded to the fiberglass well, or you're using too much heat and force with the iron. There's also a desoldering gun, but as I said in the previous video, most people won't need them and they can be quite expensive. We could spend forever and a day on the types of bad joints, but let's see the most common ones and how to fix them. Fixing most bad joints is as simple as reflowing them or removing the solder and resoldering that joint. This is the great thing about soldering, you can fix bad joints easily. But without knowing what bad joints are, you'll never know if you need to fix them or not. Having a joint with too little solder is technically a bad joint. It'll still work, but it won't be as strong, and depending on the current going through, it may not be able to handle it and burn up, although that's rare unless you're passing a lot of current. Adding a touch more solder will fix these easy enough. It's possible and very easy to add too much, in which case it'll look like a blob. This is almost always a bad thing. It's unnecessary, can put more stress on the component leg and board pad, especially if it's in a high vibration application. It also just looks ugly. The best way of fixing these is simply to remove some or all of the solder and redo them. Probably one of the worst is a cold joint. These can cause all kinds of issues, including breaking off completely. Telling a cold joint is easy with lead based, it'll look grainy and dull instead of shiny. Telling with lead free is much harder. It'll still look grainy and dull, but because almost all lead free looks grainy and dull, you'll have to compare it with other joints on the board to make sure. They can happen in a few ways. Either you're soldering at too low a temperature, your tip isn't big enough and doesn't have enough thermal mass to solder what you're trying to, or your iron just doesn't have enough power to output enough heat. The fix for the temp being too low and sometimes the tip being too small is to increase the temperature or buy a bigger tip. If your iron doesn't have enough power, then you need a higher wattage iron. Reflowing these will usually fix them. Moving components when the joint is cooling can cause a disturbed joint. Some people also call these cold joints. The fix for this is reflowing and trying not to move the component. If you can, solder the other leg, then reflow the bad joint. You'll also need to watch out for bridges. These are small bits of solder that bridge between two pads. These happen from either having too much solder on the iron or joints and touching two joints at once, or pulling the iron away towards another joint. Reflowing both joints or resoldering both joints will fix these. If there's enough room, you can also flick the solder away with the iron. Be careful doing this though, because you can cause more bridges, damage the board, or hurt yourself. You're flicking molten solder after all. Some other things that can make bad joints are cracks, tin whiskers, sharp points, often called whiskers or dingleberries. Cracks are by far the hardest thing to see, especially with lead free. These happen from vibration, cold joints, or too much heat to the board over time. Reflowing or resoldering them will fix it. Tin whiskers can be hard to see. These happen because the tin in the lead-free solder grows from the joints. They can take a number of years to decades to grow. Best way to fix them is add lead-based solder to the joint, otherwise use a soft brush to remove them. These sharp points, whiskers or dingleberries happen from the joint having no flux and the solder pulling away with the iron. Adding flux and reflowing them will fix it. There's other bad joints, but by now you should know enough to understand what to look for. Up till now I've been talking about through-hole components to circuit boards, but we also need to solder wires, either splicing them together or to other things like boards, connectors, switches, etc. Let's start with wires to wires. When we solder stranded wires, the idea is to get the solder between the strands to make them a good bond. If the solder is only on the outside, it'll be very easy to break off. Depending on the size of wire, this can take quite a bit of heat to do, and in my experience, it's a lot easier to solder them with flux on the wires to begin with. You do need to be careful with PVC insulated wires, which is most wires, because the PVC insulation melts at annoyingly low temperatures. Too much heat will cause it to melt away from your intended joint, which means you may not have enough heat shrink to cover the exposed wires. We have a bunch of ways to solder wires. The most common way is twisting them together in one way or another, then adding solder. Always remember to put heat shrink over the joints as well. You don't want to leave them exposed. You can keep them straight, twist them together, and then solder them. Put the ends together, twist them, solder them, lay them on top of the insulation on one side, then slip the heat shrink over. Hook them together, then twist each wire around the other towards the insulation. You can also use the reflow method. Tin each wire, flux on both tin wires, then reflow the solder together. Just do it better than I did in this example. Another way is by spreading the strands on both wires and intertwining them and then twisting them. This can be tricky not to get rogue strands. These twisting techniques work fine for smaller wires, but thicker wires you could have some trouble. If the wires are too thick, you might want to think about using crimps instead. Sometimes soldering thicker wires just isn't practical because of the thermal mass, so crimps are usually the best way to go about it. Again, do a better job than I did in this example. Soldering wires to boards is pretty easy. A lot of boards will have big pads, sometimes with a hole in them for the wires. You can either solder directly to those or tin both the pad and wire, then reflow them. The reflow method is also what I personally prefer to use with LED strips. I always have trouble with RGB strips because the pads are so small and it's easy to bridge them, but reflow works better than straight soldering. It's also less likely to lift the pads, which is very easy on LED strips. Another tip for LED strips: if you cut them on the dotted line and there's not enough pad to solder to, use the full pads a bit further up on the strip if you can. There's hundreds of types of connectors, but they should all be soldered in more or less the same way. Extra flux really helps with most of these as well. Most connectors, switches, etc. will have some kind of tab, normally with a hole in it. You stick the wire through the hole, half of what you've stripped, fold it flat on both sides, then solder it. It's usually a good idea where possible to put heat shrink over the joints as well. For connectors that don't have a hole for the wire, reflowing is usually the easiest way. A lot of connectors like these DC barrel ones have pins moulded into the plastic. You'll usually have to stick the wire into the well or tab for it, in this case the middle pin, but here's the fun part. With these kinds of connectors, heat it too much and the surrounding plastic will melt. If possible, use the other side of the connector to keep it all centered. There are times when you don't want to solder or tin. Most of these will be wires that go into things like screw terminals. You may not want to tin wires for a few reasons. Tinning wires can increase the resistance of that wire because of the tin section. Tinned wires can also cause some things to not have as good an electrical connection depending on how the wire is meant to be connected. These are rising clamp terminals. They're meant to clamp down on the wire. If you tin the wire, the terminal won't clamp down properly and the tinned wire may not make a good electrical connection. It's better to use bare wire that's been slightly twisted or ferrules for these. Personally, I prefer using ferrules if it's going to be a permanent connection. They're cheap enough and easy to use. Speaker wires are another time you don't really want to tin wires. The way the clamping system works sometimes means the wire may or may not make an electrical connection at all. It's better if the wire is simply twisted so it's still flexible. You can get proper connectors with braided wire, but these can be pretty expensive. Prepared wire for crimped connections is another time you never want to tin wire. The way most of these crimped pins work is they clamp down onto the strands and the strain relief bites into the insulation and sometimes into the strands. I have heard of some people adding solder to the exposed wires once crimped, but if crimped correctly that shouldn't be needed at all. Other times when you don't want to solder, you can usually use some kind of crimped connector. Spade connectors would be the most common type you'd use. These come in various sizes and can be used on various things. The most common uses are for switches. Ring connectors are also quite common for grounding, but they can be used in various ways for clamping between things. I usually replace the fork connectors on power supplies with these because they can't slip out. Finally, before I end the video, we can also do more than just solder electronics. Most people wouldn't do this, but on occasion I do, which is why I'm adding it in. Providing we have a powerful enough iron or something to help us heat the pieces and enough flux, we can actually solder things like wires or, even if we need to for some odd reason, components to metal or even metal to metal. You may be wondering why the hell you would ever want to solder a wire or a component to metal. This is my prototype foam cutter. I didn't have a ring connector small enough to fit the wire I was using, so I just soldered the wire directly to a small washer and used that instead. Metal to metal is a little bit harder because of the thermal mass of the metal may be far more than the iron. Normally you'd use a butane torch, but it can still be done with an iron. It might require some extra tools like a hot air gun or a hot plate to get the metal hot enough for the solder to bond properly. It also won't be very strong, nothing like a braze joint, and definitely not welded. That's it for this one. Sorry the video was so long, but I had a lot to cram into this. Now I'll get back to making stuff.